Join me as we calculate how an electric field shifts the quantum states of hydrogen. Spoiler alert, only one excited state makes the cut. In this problem, our first one of chapter 11, a hydrogen atom is placed in a time-dependent, so that tells you what chapter we're in, time-dependent perturbation theory, electric field E equals E of t in the k-hat direction. Calculate all four matrix elements 𝐻𝐼𝐽 of the perturbation H hat, which is E, the charge, the electric field, and Z, between the ground state n equals 1 and the quadruply degenerate first excited state n equals 2. Show that HII equals 0 for all 5 states. Note, however, there is only one integral to be done here. If you exploit the oddness with respect to Z, or only one of the n equal 2 states is quote accessible from the ground state by the perturbation of this form, and therefore the system functions as a two-state configuration, assuming transitions to higher excited states can be ignored. Okay, so this is very important to us. And you probably remember that we covered this kind of concept via selection rules back in chapter 6, okay? You may have remembered something like Laporte's rule. That's coming back in full force. So this is why we care, because the geometry and symmetry of situations can give rise to tell us what matrix elements actually need to be calculated. And if you remember from the Zeeman effect, 18 by 18 matrices or even higher states, higher energy states, they're going to be worse. So having these rules saves us a lot of time. So the challenge is go back and recall the selection rules of chapter 6 because they do make an appearance here shortly. That being said, this is a pretty hefty question in terms of keeping all the notes and bookkeeping together. So if you want the PDF, just comment and I'll send you the link to the Patreon to where you can have access. Otherwise, you'll pretty much have everything you need in the video to write up yourself. And if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with that, let's jump straight into part number 1. Okay, so stop number 1. Here we are dealing with the hydrogen atom again, in which case we must visit our old friends from chapter 4, the radial and angular equations. Since we're looking for the interactions between the ground state n equals 1, which tells us these are their adjoining quantum numbers, we only have one equation. But for the first excited state n equals 2, we have 4 of them, just the plus or minus on this m number. Okay, so let's first set up all the possible wave functions from the quantum numbers using the tables, and we see that we get these composites here. Again, in the PDF, didn't see the need to put them in the video outside of this quick picture. So for us then, if we want to use these and find the matrix elements, we need to find them via equation 11.13, and we could tell that the interactions between the ground state and the first excited state, we're going to have 4 or 5 different calculations, so let's just jump to it. Of course, this is a pretty easy thing to remember, especially from chapter 7, where we're finding the matrix elements. So here then what we have is the ground state, first excited state with 0, 0. We see that we can put the wave function in there. But remember that here that z is a Cartesian coordinate, and we can put that in terms of the spherical coordinates with r cosine theta. Then of course we can bring the constants out front. That includes the normalization constant, so we tidy that up. But we realize again that the inner product here is that of an integral over all space. Okay, so if we color code this up, we see what happens in phi with the complex conjugate of the first wave function, keep the argument in the middle, so the perturbation, and then we have the wave function on this side, and then we of course have our differential element, color coded up so you can see what parts go to where. Thanks to Fabini's theorem, we could split that. But if we look at it very carefully, we see that this thing is what we would say odd in z, meaning that we could just write this theta integral as 0 because that's what it evaluates to. If you did a u sub on this and got rid of everything, fair enough, change the limits, this, that, and the third, what you would end up with is a did a u sub on sine, you would end up with a 0 down here and a 0 up here. An integral from 0 to 0 is 0, so it doesn't matter what happens. So because this thing's 0, we don't care what happens with the purple and blue, okay? So that's one way to use the symmetry here to help us, and we'll keep invoking this idea time and time again throughout this chapter. Moving on to the ground state with the next highest excited state, so psi of 2, 1, 0. Again, set it up the same way, let it run through. We see we have the different wave function on this side though, different one here. Channel it all out. Now, this one's a little different because we actually can evaluate this, okay? So when we take all our constants outside, just 32 is really just 16 times 2. We do that because we can just get a square root of 2 here. That 16 goes to 4, and that will simplify later. Upon cleaning up all this nonsense here, we have 1r, 2r, 3r's, or 4r's here, so that gives you r to the 4th here. Add the exponentials, that's 1 and 1/2, that combines to 3/2. Cosine, cosine, sine, that gives you cosine squared, sine squared, and phi's by itself, perfect. So we clean up all the constants out here. Note here that a cubed turns to a to the 4th due to this r over a, so that's nice. And then from here, we just have to evaluate. The phi integral goes to 2 pi, theta goes to 2/3. This is an exponential integral, which instead of doing repeated parts, we just use the table in the book. So r's to the 4th power, so we have 4 factorial. Then we're dividing by quote a in the book, just a label. And then we have n plus 1 up here, so we're just checking the form. And now it just turns into simplify. Pi and pi cancel. We see here that when we go ahead and expand all of this, we have 4 times 3 times 2 times 1 from the factorial. And then we could apply this 5th power to 2a and 3 independently. Upon doing so, we see that this 4 and that 4 cancel. Green 3 and blue 3 cancel. All a to the 4th down here cancels with 4 of them up here. So then we can combine these into all one term. Note here that e, little e, big E, root 2 stay out front, no big deal. Then we have 2 up here that is being joined together by 1, 2, 3 other 2's. 1, 2, 3 other 2's, so that simplifies us down to 2 to the 8th. Since we took 4 away from the power, we're left with a to the 1, so that simplifies to a. And then we just have this nice little numerical thing here, 2 to the 8th over 3 to the 5th, root 2, E, little e, charge E, the electric field E, and then A. So not too bad there. But since we were told there's only one integral to evaluate, what do you think's going to happen with the other two? All right. So here then, what we see is that when we run the same game plan, it's pretty much the same way through, okay? Or with this wave function, note that we have a positive one here, so we need a negative on this normalization constant here, which is where I get a negative there, and a plus sign in the exponential. So running it through, put it in the integral, simplify it. Oh no, we end up with a theta integral again that is not going to be conducive to us to evaluate, so we get a 0 there, so the whole thing is 0. And just as you would expect, if this works for the plus sign, it's going to work for the minus sign as well, the -1. Negative there, positive here. You end up with the green integral that is odd with respect to sine. So that gets canceled away, easy enough. So we like to see that. And so, what we did was just find everything, and we used a basic symmetry argument here. But we can go ahead and kind of abstract that thing even more and look at what happens with the z arguments and what's even and odd, and that'll save us a lot of time. Okay, so if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. So with that, let's go ahead and jump to stop number 2, where we're evaluating the wave functions with themselves, so the main diagonal elements. For anyone who's keeping track, here's a summary of that, just to keep it all in one place. So now the concept of even and oddness comes in with respect to the integration over all space. which leads to symmetric bounds. Again, negative infinity to positive infinity, things like that. Or if you convert that to spherical, you saw how that happened and pretty much just targeted the theta integral. Okay, so we know that what happens with symmetric bounds is that odd integrands over symmetric bounds evaluate to 0. That's what we were actually trying to showcase. Okay, kind of hard to see in the spherical landscape, but we notice that the only thing that equaled 0 there was the theta. So if we're odd in z, that tells us that we're going to be, quote, odd or antisymmetric in theta, which is very, very important to us. Okay, so from here, knowing that we're going to have to look at the inner products again, we observe that the matrix element for this setup with the wave function with itself, same thing, e to the a, the triple integral over all space. We have a conjugate here on the left side, z, and then the wave function. Z does not operate on anything, it's just a position, so we can just move it forward. So really all we're looking for is the magnitude of the wave function. Now, what we have here is that z is an odd variable, meaning that it will make a function odd. So what we really need to do is showcase whether this psi is even or odd. Because if we have an odd times odd, that's going to be even. If we have an even times an even, that will be even, all right? And then if we have odd times even, we're going to be odd. Okay, pretty easy there. Okay, so let's see if we can find out what this even and oddness is and see what it does to our integral. Starting with the ground state, we see that finding the magnitude squared, since we're all real, it just equates to squaring everything, which is what we see here. But if we plug in the Cartesian equivalent to r, which is square root x squared plus y squared plus z squared, we note that this function is the same whether I plug in a negative value for z or positive value for z, because that's square. Okay, so in general, we just say this whole thing's even. Okay, and because that's even, when we multiply by z, odd times even is going to make it odd, and we'll see that that goes to 0. Oops, yep, that's equation 1.13 for those keeping track. Now let's move on to the other couple states. All right, so for the first excited state with L equals 0, ML equals 0, we have a square, again, all real, so it just equates to the magnitude, turn it into a square again, square everything, plug in the R definition, square root. Again, if I plug a negative value in, I get the same value if I plug a positive value in for z, x, or y. So we're even times even. This thing's even, so we get an even. Moving on to L equal 1 for N equals 2. Again, we're all real inside, so let's go ahead and just be aware here that that cosine we're going to have to sub out for Cartesian soon. Okay, so square everything. We see we get a square there, no big deal. But we know that cosine, or z was equal to r cosine, so cosine is equal to z over r. If we square that, that cancels this r with that r squared, so what we're really left with is z squared times the exponential. Z squared is an even function. This exponential is an even function, so their multiplication is also even. Okay. Now, the first three weren't really that hard to deal with. The last two is going to be tricky. Okay. Not to mention here that we have magnitude, and we have this purple term here, which is complex. So we're going to end up dealing with a lot of different ways to look at this, but we have to remember that the conjugate here in the magnitude does play a role. Okay. So let's simplify this down, get out the constants and things that we can simplify now, and see what happens. So taking out all the constants and real parts that don't change anything, right, we get all this, the plus or minus plus vanishes because it's a magnitude. And then we see that simplifying them, good to go. What we need to do is really target this exponential. In theory, we should know that this thing cancels, but then we would be left with the sign here that needs to be constructed. And instead of doing that, it'd just be easier to keep this in here. Substitute cosine phi plus or minus I sine phi. And by doing that, we can distribute r and sine into that, which is what we do here. But upon doing that, what we realize is that this is the x coordinate, this is the y coordinate in spherical coordinates. So we just put x plus or minus I y. That is a fantastic simplification that if you didn't see it on the first run or first go at this, this saves you a lot of time actually. And we will use this result again later in another question, oddly enough. So then from there, knowing that we need the conjugate times the thing itself, just switch the sign on the I, we're good to go. And now if you multiply this, you get the cross terms vanishing. So you get x squared minus I squared y squared, which turns into a positive y squared. So since the exponential is even, and this thing over here in green is even, we know that we're even across the board. So what we see here is that all of the wave functions that we're curious about, again, be careful, the plus or minus indicates two different wave functions. All 5 wave functions are even. And from here, it's very quick to see what happens in the integral, because if we look at the ground state, what we observe then is z is odd, the exponential is even. We get rid of all the coefficients here, no big deal. This tells us that this product here is odd in z. And so for odd over symmetric bounds, then we integrate to 0. So it doesn't matter what happens in x or y because we're multiplying by 0. And that makes us save a lot of time. This is the symmetry argument, and what we will see recapped again when we deal with the selection rules specifically for the forbidden states. And then here, we just walk through the same thing for the second ground state, the first excited state with L equals 0. We see that, again, odd in z, even wave function squared, or even magnitude squared. Whole thing's odd, so we evaluate to 0. Odd, even, 0. Odd, even, 0. So in summary, every single one of these is an odd integrand, so we evaluate to 0 matrix elements. And that is a wonderful sign to see because it's less work for us. All right, well, that was a fun little video, bringing back things from chapter 4, from chapter 6. Now we get to see more specifically that these two-level systems are very, 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 very much the case of what is needed for time-dependent perturbation theory. What we'll see shortly in excruciating length and detail is how this thing works, because we remember that for a complete setback in chapter 2, we were able to split up the time dependency into a separate exponential. And that exponential could be on the base wave function, which is position dependent, could be consumed in the coefficients of a linear combination. And those coefficients are what are going to make or break this entire section. So get ready for some arduous, painful stuff here soon, but something that is arguably the most important to any future in quantum mechanics, because perturbation theory, you can't live without it. So thank you all for watching. Share this with a friend who's also curious about science, and let's grow this learning community together. Thank you again for all the supporters of this channel. You make this possible. Please consider supporting this channel by subscribing and sharing this curiosity, or joining our Patreon village and or book drive, whatever you can do. It will be appreciated. So thank you, thank you, thank you. As always, thank you for watching, and until next time, stay curious.